Hello, my name is John Cody. I'm back with part 3 of exploring the quadria of the projective quadrilateral. So we're in this setting where we have a projective triangle, A1, A2, A3 with side quadrants equal to 1. All three side quadrants are equal to 1, and all three spreads at A1, A2, and A3 at those points are equal to 1. And in addition, we have a point inside the projective triangle A1, A2, A3. We have a point inside the triangle A4. And what we did previously is we connected the points of the triangle A1, A2, and A3 through the point A4 inside the triangle. So we have these lines A1, A4, A2, A4, and A3, A4, and they're extended to the edges. And in addition, we worked out the values of, we have side quadrants of A, B, 1 minus B, F, 1 minus F, 1 minus A. So what we're going to do next is we're going to, from those lines we had previously, we had points, they became points A5, A6, A7, and when we connect those points together, we form this triangle inside with quadria A4. So the quadrants between A5 and A7 is Q, the quadrants between A6 and A5 is P, and the quadrants between A7 and A6 is R. And the quadria of this triangle down here is A1, this quadria of this triangle is A2, the quadria of this triangle is A3, and the quadria of the triangle in the middle is A4. So using projective Pythagoras formula, we're going to get values for P, Q, and R. So because the spread here is 1, we can get the value of P from the projective Pythagoras formula, which is A plus B minus AB. So P is A plus B minus A times B. Similarly for Q, because the spread is here, we could apply the projective Pythagoras formula, and that's going to be F plus 1 minus B minus F times 1 minus B. And the same applies for R. Because the spread here is 1, we can apply the projective Pythagoras' formula, and that's going to be 1 minus A plus 1 minus F, all minus 1 minus F times 1 minus A. That's the value of R. So these are three quadrants. And we also had from previous results that we came up with the formula for F in terms of A and B. So F was A times 1 minus B, all divided by A plus B minus 2AB. And we're going to use the projective cross law to calculate the quadria of this projective triangle A5, A6, A7 to calculate A4 using the projective cross law. So that'll be A4 minus quadrants is P minus Q minus R plus 2, all of that squared is equal to 4 times 1 minus P times 1 minus Q times 1 minus R. And we're going to substitute the values for P, Q, and R up here into this equation, and we get this result only in terms of A and B. So the quadria of A4 is determined in terms of just the quadrants is A and B. From this formula and substituting for these values into the formula, we get A4 is AB times A minus 1 times B minus 1, all divided by A plus B minus 2AB. So next we're going to sum up the quadrias A1, A2, A3, and A4. And so A1 is going to be A times B times the spread S. So that's just A times B. A2 is going to be F times the spread of 1, which is 1 times 1 minus B. The quadria A3 is going to be 1 minus A times 1 minus F. And the quadria A4 is the result we got right here, is AB times A minus 1 times B minus 1, all divided by A plus B minus 2AB. And when we add that all up, it becomes A squared B squared minus A squared B minus AB squared plus 3AB minus A minus B, all divided by 2AB minus A minus B. So the sum of the four projective triangle quadrias, A1, A2, A3, A4 is this, and that does not sum to 1. The numerator does not equal the denominator, so that does not sum to 1. So since A2, A3, A1 plus A2 plus A3 plus does not sum to 1, you cannot calculate the general quadria of quadrilaterals formed from two projective triangles with a common edge by summing the quadrias of the two projective triangles. So what that means is, if I cannot get the quadria of this quadria by summing this A1 plus A4, so the quadrilateral A3, A5, A7, A6, this quadrilateral cannot be arrived at by summing the quadria of A1 plus A4. Similarly, for this quadrilateral A1, A7, A5, A6, you can't just sum the quadria of A3 with A4, and same for A2, A7, A6, A5, that quadrilateral, you cannot just sum the quadria of A2 and A4. So in general, yeah, you cannot just sum quadrias of projective triangles to get the quadria of a projective quadrilateral. Okay, next we'll look at tessellating it a different way. So we had this quadrilateral, or this triangle with points A7, A5, A6, and we're going to tessellate this this triangle in this way. So we're going to have lines A6, A7, A7, A3, A7, A5. Okay, so we're going to have quadrants, projective triangles with quadrias A1, A2, A3, and A4. Okay, so next we're going to calculate the sum of the quadrias A1, A2, A3, and A4 of the four projective triangles, and we get A. So A1, A2, A3, A4, we're calculating the sum of these quadrias. So A1 is 1 minus F times 1 minus A, because the spread here is 1. A2 is A times the spread 1 minus F times the quadrants of this line segment, which is 1. So that's going to be, A2 is going to be A times 1 minus F. Same thing with A3, it's going to be the quadrants of this line, which is 1 times F times B. And A4, it's going to be, the quadria of A4 is going to be F times the spread of 1 times 1 minus B. And when we add these four up, these four quadrances up, we get this expression. And you see everything cancels except for the 1. So this results in a quadria of summing the four projective triangles to give a result of 1. And that's equal to the quadria of the larger triangle, projective triangle A1, A2, A3. So what's the difference between this configuration and the one where we tessellated by connecting A5 and A6 instead of A3 and A7? Like previously, we showed that if we tessellated it with using a line between A5 and A6, then that did not sum to 1, but in this case it does sum to 1. So the only difference is between the two triangles is that this one there's a spread of 1 here, so we divided the triangle where the spread is equal to 1. So f plus 1 minus f is 1. So what we can say is the quadria of the projective quadrilateral A5, A3, A6, A7. So A5, A3, A6, A7, this quadrilateral is the sum of the quadrias A2 and A3. And this leads to the conclusion that if the spread at one of the projective points in a projective quadrilateral is equal to 1, so if this projective quadrilateral has a spread of 1, then the quadria of the projective quadrilateral can be calculated by tessellating the quadrilateral at the projective point and summing the quadrias of the resulting two projective triangles. So we tessellated the quadrilateral at this point by putting this line in. And then we can just sum the quadria of the two projective triangles. So I'll present the summary of the Okay, so I'll present a summary of the results we have so far for calculating the quadria of a projective quadrilateral. So result 1 says that if you have a quadrilateral A1, A2, A3, A4 that has one of the spreads equal to 1, then if you tessellate it, the quadrilateral by at the point 1, or where the spread is equal to 1, so if we tessellate it by adding this line where the spread is equal to 1, then the quadria of A is equal to the quadria of A1 of the two projective triangles that are formed when you do the tessellation. So the quadria A is equal to the quadria A1 plus the quadria A2. So that's the first result. The second result for calculating the quadria of the projective quadrilateral. So if a projective quadrilateral has two adjacent spreads both equal to 1, so here we have a quadrilateral A1, A2, A3, A4, and two adjacent spreads S1 and S2 are both equal to 1. If you have this set up, then and you know the quadrants is A, B, and C between that's adjacent to these spreads that are equal to 1, then the quadria of that projective quadrilateral is A times B plus B times C minus A times B times C. So the quadria A is AB plus BC minus ABC when S1 equals S2 equals 1, when two of the spreads are equal to 1. And thirdly, we found that result 3, so it says if you have a projective quadrilateral A1, A2, A3, A4, and 3 of the spreads are equal to 1, then you can calculate the quadria of that quadrilateral just by just knowing the two of the side quadrants that are between the three spreads that are equal to 1. So Quadrea, this side A is between these these points where the spreads are 1, and B is between these points where the spreads are 1. And if that's the case, then you can use this formula here for calculating the quadria of the projective quadrilateral, just knowing the two side quadrants is. Okay, so that's it. So what I've demonstrated is that if we have a projective quadrilateral and we know if at least one of the quadrants or one of the spreads in the quadrilateral are equal to the 1, then we are able to calculate the quadria of the projective quadrilateral. And we had 3 different formulas depending on how many of the spreads were equal to 1 in the quadrilateral. Okay, that's it. That's the end of part 3.